Yes, Lewis in at the end. Adam Thompson.
Thank you very much, Madam Deputy Speaker. As I believe, as the Secretary of State said earlier, I think the first metrologist elected to this House in history. It gives me great pleasure indeed to rise today. In fact, Madam Deputy Speaker, I took the liberty of checking Hansard before today, and until the Secretary of State said it earlier, I was the only person in history to use the word metrologist in the House of Commons. So I'm very proud to be here today, and I'm prouder still that the Labour government has brought forward this bill featuring metrology in our first year of a new government. Despite the majority of debate today, Madam Deputy Speaker, has focused on the product regulation side of this bill. Given my background, I'd like to focus on the metrology. Prior to my election to this place, Madam Deputy Speaker, I was at the University of Nottingham, throughout which I was research active in metrology for advanced manufacturing, beginning with my PhD and continuing through several more years as a research fellow and latterly a senior research fellow. But like most people I have known in my life, when I first began my PhD, I had absolutely no idea what metrology was. Indeed, Madam Deputy Speaker, I'm sure several colleagues around this room didn't know what it was before today, and I fear still don't. If you'll allow me, though, Madam Deputy Speaker, I would like to provide for the record some explanation as to the nature of my science and explain why, contrary to popular assumption, it has absolutely nothing to do with clouds. The international standard... Yes, please do forgive the terrible pun there. The international standard, Madam Deputy Speaker, the Vocabulaire International de Metrologie, formally defines metrology as the science of measurement and its application, noting that metrology includes all theoretical and practical aspects of measurement, whatever the measurement uncertainty and its field of application. It isn't, Madam Deputy Speaker, the branch of science concerned with the processes and phenomena of the atmosphere, especially as a means of forecasting the weather, which is, of course, meteorology, something I have explained almost every day of my professional career. Metrology broadly encompasses the various fields of research that seek to develop the science and technology of measurement, be that measurement of any of the 7 base quantities from the Système International des Unités, the SI, or any of the units derived from these base quantities. The 7 base quantities are, of course, length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. The great physicist, Lord Kelvin, once expressed, "To measure is to know," and also, if you cannot measure it, you cannot improve it. These sentiments are rarely more applicable than in the advanced manufacturing industry, where we are interested both in ensuring that a manufactured component meets the dimensional specification laid out by its designer and in constantly improving upon existing products. Metrology is a science that fundamentally underpins all other science. Without tools that allow us to measure, allow us to know, we cannot gain any understanding into the world around us, nor can we improve upon it. In the fundamental scientific pursuit of understanding our universe, we are most often concerned with the first of the SI-based units, the meter. The meter is defined, Madam Deputy Speaker, formally by taking the fixed numerical value of the speed of light in a vacuum C to be 299,792,458 when expressed in the units meters per second, where the second is defined in terms of the cesium frequency. This definition changed, in fact, very recently. It came into force in 2018. But the meter is more simply described by its older definition, and it's simply the distance travelled by light in a vacuum in a time interval in seconds of 1 divided by the speed of light. In my opinion, Madam Deputy Speaker, the meter is one of the most beautiful creations in science, defined by light itself, and a creation which allows us, in turn, to create everything in our world. At the start of our debate today, Madam Deputy Speaker, the Honourable Member for New Forest West asked the House, when did weights and measures become metrology? Well, I'd like to explain now, Madam Deputy Speaker. The answer to that question is several thousand years before the Common Era. Behind every great scientific advancement in history, there has been a metrologist. Behind the pyramids, There were the first standardized unit of measurement, the royal cubit, defined as the length of the pharaoh's forearm, as measured from the tip of his forefinger to the base of his elbow. The cubit was a technology so advanced that it allowed the ancient Egyptians to position the building blocks of the pyramids to an accuracy almost equal to modern methods. And thousands of years later, there remains speculation as to whether they were in fact built by aliens, because of how incredible an achievement that was. They were, of course, not built by aliens, Madam Deputy Speaker. They were built by metrologists.
Will the honourable gentleman give way?
I will gladly give way.
I am grateful at the start of this debate, as a fellow scientist, I wondered what the difference was between mensuration and metrology. Because when I was an undergraduate, we did not use the word metrology. It seems to be a new word. Maybe the honourable member can enlighten the chamber.
I thank my honourable friend for his intervention, certainly. Not a new word as far as I'm concerned. I believe it was brought into common parlance in the Victorian era. To move on to some more examples, Madam Deputy Speaker, behind the James Webb Space Telescope, something more modern than the pyramids, the James Webb Space Telescope now takes images of our universe more than 13 billion light years away. Images more deep, more brilliant and more beautiful than anything we have ever seen. There is a construction behind this of a 6.5 metre mirror, flat to within just a few tenths of billionths of a metre, from its highest top to its smallest valley. If we were to expand the size of this 6.5 metre mirror to the size of the Earth, the highest mountain to the deepest valley would be on the order of the height of my hip. Behind the discovery of gravitational waves, Madam Deputy Speaker, there are a series of interferometers, kilometres in size, that can detect signals from noise at levels considered unachievable throughout human history until the past 20 years or so, capable of listening to the collision of black holes across space-time. I would gladly give way.
I hesitate to interrupt the honourable gentleman because this is a wonderful contribution to our affairs. It is indicative of the beauty of science, and we hear too little about that. But before he rushes, hurtles, one might say, into the future, could he say a word, too, about the peculiarly British measurements which informed my childhood? Things like pecks, perches, rods, bushels. For each of those, in the way he's described, was rooted in the way that he described.
For his intervention, Madam Deputy Speaker, and happy to explain. I mean, these particular forms of measurement are not in common use anymore, but of course, many members, and right honourable members in the House, will have grown up with these. They are broadly, the ones that are still in use, defined in the modern parlance, but I think it's important to remember that the modern metric system accounts for all of these heritage measurements. The common inch, for example, formerly defined as 25.4 millimetres. The pint. I apologise to members across the House. It's important for me to let you know the pint is formally defined as 568 millilitres.
You have to declare an interest.
These heritage measurements, and indeed the entire imperial system, is now referenced onto the metric system. Defined very simply, the imperial system is the metric system. And there's no reason why we shouldn't use these historical measurements. Where useful, they are perfectly valid. But they are formally defined within reference to the modern metric system. And I'm going to talk about this shortly. Metrology, Madam Deputy Speaker, lies at the heart of everything we know, from telescopes to speed cameras to knee replacements or jet engines. Every single thing made by human hand was designed first, constructed second, and then checked by a metrologist to ensure it met its specifications. If we cannot know it, we cannot improve it. However, ensuring parts meet their specifications is not simple, as each measurement, dimensional or otherwise, has an associated measurement uncertainty. That is a non-negative parameter characterising the dispersion of the quantity values being attributed to the thing being measured, based on the information used. Estimation of measurement uncertainty is a complex procedure. It formed much of my career prior coming to this place, and is usually performed in line with the Guide to the Expression of Uncertainty of Measurement. Uncertainty estimation is generally performed by making measurements that are traceable to the definition of the SI metre when we are concerned with the metre. Again, the Vocabulaire International de Metrology defines traceability as a property of a measurement result whereby the result can be related to a reference through a documented, unbroken chain of calibrations, each contributing to the overall measurement uncertainty. Traceable measurements allow for the successful estimation of uncertainty and are generally a base requirement for the verification of manufactured goods. Traceability is considered by the international community as the only means by which evidence can be provided towards a given product fulfilling the requirements set out by its designer. To provide an example, let us consider, Madam Deputy Speaker, a length measurement made between, say, two faces of a manufactured part. Let's go for a Rubik's Cube. Imagine I'm holding a Rubik's Cube because I couldn't possibly have brought a prop, Madam Deputy Speaker. The length between two faces could be measured by a caliper. This caliper would be calibrated using a measurement artefact, most commonly a metal cuboid called a gauge block. This gauge block would then in turn be calibrated by a more accurate instrument, which is in itself calibrated using a more accurate gauge block. This more accurate gauge block will then be calibrated in reference to an optical interferometer using a laser source. The laser source is finally calibrated against the iodine stabilized laser that is used to realize the definition of the meter.
Good luck, Hansard.
And so traceability is established, Madam Deputy Speaker, from the shop floor measurement all the way up to the definition of the meter by this unbroken chain of calibrations. And we do this in every... I will gladly give way to my honourable friend.
I felt impelled to intervene because my honourable friend is giving a hugely passionate speech about a subject he clearly knows so much about. And I would ask him, how can he help to inspire the next generation of meteorologists and be as inspired about the topic as he clearly is?
That's very kind. I thank my honourable friend very much for his intervention. Indeed, if he wishes, I've got a 97-slide lecture here that I'd be more than happy to deliver afterwards.
Nobody wishes for the 97 slides. Mr. Thompson.
Don't worry, Madam Deputy Speaker, not one for today. I'm nearly finished. Each stage of the traceability chain has some discernible uncertainty, Madam Deputy Speaker, which generally increases as we move down the chain, as instrument accuracy decreases. Estimation of uncertainty, each link in the chain, is essential. It is impossible to have a traceable measurement without the inclusion of an uncertainty with that measurement. Traceability, when applied in manufacturing, allows us to create anything we can imagine within the confines of our chosen manufacturing process. It is the cornerstone of our modern manufacturing industry. In this bill, Madam Deputy Speaker, the government seeks to update metrology regulations and the means by which those regulations are enforced. We have heard at great length different opinions as to that process, but the government are today ensuring conformity with the SI system, ensuring uniformity in measurement, sale, monitoring and quantity of goods. They're ensuring further that the Secretary of State and other appropriate bodies have the powers that they require to inspect and enforce that conformity. This bill will ensure that the UK law is updated to recognise new or updated international regulations to keep us at the cutting edge of science and regulation. Members said earlier in the debate how the UK was at the forefront of regulation. I spent many years myself on standards committees working through these things. Every standards committee I ever worked on fed into the British standard, which fed into the European standard and the international standard. These are the frameworks that we are updating today to ensure that we remain at the forefront. This is going to mean cost savings for business and it will promote regulatory stability. Madam Deputy Speaker, finally, the provisions laid out in this bill continue the work begun by the ancient Egyptians, the work that allowed us to build everything from the Great Pyramids to the phones in our pockets, the paper that we hold in our hands, or indeed the very floor on which we stand today. The work that we are doing today ensures that the bulbs that light this room are of an appropriate brightness, that the air that we breathe and that surrounds us is of an appropriate temperature, and that we can finally get a fairly measured full beverage in the pub of exactly 568 millilitres.
Will the member give way?
Madam Deputy Speaker, I support this bill wholeheartedly.
Follow that